Hello and welcome to another LeetCode video. Today we're going to be working on search in a sorted array 2. And so this is similar to the last problem where you have some array and it could be rotated, it could not be. So in this case it is rotated in the example. So you have something like this. And we are trying to find the target in it. So in this case it is in there, and then for the 3 it is not in there. So the difference between this and the last problem is here we have duplicates. So let's just remind ourselves again what we did if there are no duplicates. So if there are no duplicates, it's pretty straightforward. Well, it's not super straightforward, but essentially you can find the lowest value in the array because the array is going to look one of two ways. It's either going to be completely sorted where it will just be strictly increasing like this, or it will be rotated where it will be increasing and then there will be a drop and then it will be increasing again, right? Like in this case, it is increasing, drop down to the 0, and then increasing again. So we are on the second one. But either way, if it's this or this, it's going to be kind of the same. For this, you can just check right away. You can just check this value and the last value. And if the left value is less than or equal to the last value, then you know it's this format. Otherwise, it's this. And for this format, what we basically did was for any pivot point, we just compared it to the leftmost value in the array. And then if it was greater, that means we have to be in this chunk of the array. So we haven't yet rotated. So then we can check, we can just get rid of this chunk and then check this chunk and so on. So that's how we did it for the last one, right? And that worked. And then we got some rotation point. And then we just divided our array into two. So we have divided our array into this array and this array. And then we knew because if you have this index, you know the range of numbers in your two arrays. So this would have to be 0 to 2. This would have to be 2 to, well, actually with no duplicates. Let's say there is no 2 here. So this would have to be like, let's say 5 to 6. And then you just simply find out like what array your target has to be in, and then you just do a binary search of that array for your target. That's what we did for the last one. But now for this one, there's going to be problems. And the problems are going to be with the duplicates. So let's just say, for example, we have something like this. We have something like just all ones. And we're going to add a little bit to this, but let's say we have something like this, and we have a left and a right still, and we have a pivot. So here the problem is like, you don't really know where to go, right? So if you think about it, let's say our target is 0. We can just put a 0 anywhere we want. Like if we get this pivot, we don't know if our target's on the left, the right, or who knows. Because our target could be here, 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 it could be anywhere. And these are all valid rotated arrays, right? Because you just have, it's increasing and then the ones are a duplicate. And you can even have like multiple zeros right next to each other and so on. So the problem with something like this is you don't really know where to go. And it's pretty much impossible. I mean, I think, well, you pretty much have to just like linear search where to go, because there is a problem on LeetCode where you're trying to find like the start and end index of a number in an array, right? Like you have some sorted array where it's like 1, 2, 3, and then you have like a bunch of 5s, let's say, and you're trying to find like the start and end of a bunch of 5s. That's doable, but the problem is here, it's not sorted because you can have like zeros here or something which wouldn't make it sorted, or zeros here, or like just like hidden numbers and you don't even know where they are. So that's problematic. You can even have something like this. You can even have like 2, 3, 4 over here. And then it's like, okay, what do you do with that? It could also be over here, So like, it's not as straightforward. So in this case, we have to change the way we're doing our problem. And we're no longer going to look for rotation index. We're actually just going to look for the number right away. And then we're also going to have a case where this is the case where our pivot equals our left. You could technically check for both. There's like a bunch of ways you could do this. They all end up being the same time complexity. Because if you're in a loop and you do like left plus plus and right minus minus together, that doesn't really save you anything. You're still doing two operations. So if you do two operations, n over 2 times, or one operation n times, it's still the same thing. Okay. So we need to figure out how to do this better. And so we're going to actually break this down. We're going to first do the problem that was given, and then we're going to come back to one of these. So for this, instead of looking for a rotation index, because we know we can run into some of these weird cases, and if you were like me, you may have tried to like do this. You may have been like, okay, well, let's just see what happens with duplicates with my old problem, and what are my issues, and then you got one of these weird test cases where something like this, and then it was like, okay, well, maybe I can just linear search for my pivot in both directions or something, and it gets kind of tricky really fast. So instead, there's like a cleaner way to do it, and that's what we're going to go over. So essentially what we're going to be doing is we're going to be looking for, so remember, an array can either be like this, and every subarray is going to be like the two. It's either going to be strictly increasing, or it's going to be increasing, and then there's going to be a rotation index, and then it's going to be increasing again. So for any subarray, that's the case. Like for this, it is increasing, then we have drop, then increasing. We can check some more arrays, like this whole array, increasing, drop, increasing. Then if we take like this subarray, it's just increasing. So those are the two conditions. It's either going to be strictly increasing, or there will be one drop, right? Okay. Now, obviously, with duplicates, it's not going to be, I guess it's not going to be like strictly increasing. You might have like similar stuff. So you might have like a flat region, and then it'll be increasing, and then a drop, and then like there might be some flat regions like this, right, with duplicates. So that's the case, but that's going to be totally fine for our problem. Like that'll be fine. We really just need to know, even with these flat regions, there's still going to be like a left side, a drop, and a right side, and that's what we care about. Or there will just be a left side and no drop. Okay, so let's actually look at these pivot values, and let's look at our condition. So if we have a left here and a right here, our pivot will be this value here. And so what we need to check, and let's say our target's 3 in this case. Let's not do 0. So what we need to check, actually we missed one number. So let's actually redo this and add, there was another number here, and I think this will work out better. So there was a 0 here as well. There we go. Okay, so yeah, so we're gonna look for 3, because if you look for 0, we're gonna find it right away. So it's obviously not gonna be a great example. So this is gonna be the pivot, and our target will be 3. Okay, so now we're gonna check for a couple cases. So we're going to check, is the pivot greater or equal to, or less than, or whatever. So actually first we're going to check, is the pivot equal to the target, right? So it is not. So that's what we're going to do. Pivot does not equal target. Okay. That's going to be our first case. Then we are going to check, does the pivot equal the middle value? Or sorry, the left value. So are these two equal? And if they're equal, that means you can have a bunch of cases, and it's kind of hard to say which one, right? Like, for example, you can have something like this whole array is 2s. In which case, you don't really know where to go. You might be done, but you might also have like a 0 here. You might have a 0 here. These are all valid. 0 here. You can have like a 1. You can even have like a 4, 5, 6 over here, you know? So if the pivot equals the left value, we're just going to say, let's just increment the left value until it's not, right? So if the pivot is, so like if we have this case, or actually we're not going to do this one yet, but yeah, if the pivot is equal to the left value, let's just increment the left value, because we don't really know where to go, so we're just going to manually increment the left value. So we're saying like a binary search wouldn't be helpful here because we don't know where to go, so let's just increment the left value. And the reason we can do that is we're guaranteed that the answer won't be the left value, because we are checking for the pivot being equal to the target to begin with. So if the pivot is not the target, and let's say the pivot is 2, if the pivot is not 2, that means this can't be the target. So we're getting rid of numbers that we don't really care about. So if we increment this, we got rid of something we don't really care about. And we can just do this until the left does not equal the pivot. So we can just do that in a while loop. If you don't do it in a while loop, you can also just do it once and then move on to the next iteration. It's all going to be the same time complexity, really. If you think about it, you can also like, I think, yeah, in some other, or yeah, you could also check the left and the right, but it's going to be all the same time complexity. It's the same thing. Okay, so now that we did that, our pivot does not equal the left value. So now we need to check, is the pivot greater than the left, or is it less than? And if you think about it, remember our array looks like this. It might have some flat region, but that doesn't matter. Then it has a drop, then it has this. So if it's greater than the left value is over here. If the pivot is greater, that means the pivot has to be on this like left side of the answer. If it's less than, that means the pivot has to be on the right side, right? Because we've hit the drop, and we did hit the drop here. So the pivot is less than left here. Now we're going to check for the target. Is the target greater than the left, or is it less than? So the target is greater than the left. That means the target is on, so the pivot's over here. The target is actually on this side of the array. And so because the target and the pivot are on different sides, we know that we can just, like the pivot's over here, the target's on the left. So the target has to be somewhere in here if it's in here at all, right? And so we can say, okay, well, if the pivot's on the right side of the answer and the target's on the left side of the answer, then let's just get rid of all this and let's make the right over here. Okay? So hopefully that makes sense. We have two sides of the array. It can either have only one side, which is going to be the left side, it's strictly increasing, or increasing with some flat regions, or it will have this drop. So if they are on different sides, we just simply find like which side is the pivot on, which side is the target on. And so if it was reversed, if the pivot was on this side and the target was on this side, then we would just take this right side instead. Now we took the left side. Okay. So now in our next iteration, we get a pivot again, and we say, okay, is the pivot, let's actually get rid of all this. Is the pivot greater than or less than the target? So let's take a look. So the pivot, or sorry, not the target. First of all, we have to compare the pivot to the target. It is not equal. Then we have to say, is the pivot greater than or less than the left? So it's actually greater than the left. And so if we draw this picture again, the pivot has to be over here, right? It's on this increasing side because the left is over here. Now what about the target? So the target is also greater than the left, right? They're both greater than this 2 value. So then now they're on the same side. So now there's two scenarios. They're not equal. So the target either has to be here, has to be on the right side of the pivot, or the left side of the pivot. And now we're just doing like a linear search, like a binary search in a sorted linear array. And so here, our target is smaller than the pivot, right? So pivot is greater than the target because our pivot is 5. So if our pivot is greater than the target, that means the pivot is here and the target is here. And so we're going to want to delete the right side because we're going to want to go left, right? And similarly, if the target was on the right side of the pivot, but they're on the same part of the array, then we would delete this side, right? So that's two cases. They're either different, they're on different sides of the array, and then you just delete whatever side the target isn't on, or they are in the same side and you just figure out like where's the target relative to the pivot, and that's just a normal search in a, like if you had a problem that this array was sorted, it would be pretty straightforward, right? Like if you had like 0, 0, 2, 3, 5, 6, let's say, or 2, 2, 5, 6, and you got a pivot value here and your target was 3, that would be a pretty straightforward problem if you knew the whole thing was sorted, because then you could just say like, okay, my target's over here, let's just delete this. And so that's essentially what we are doing for the second case, where they are on the same side of the array, like they are here. So our target has to be to the left side, and so we're going to delete this, and we're going to say, let's make our right value here. Okay. And now let's actually do the last one. So our pivot is 2. Is it less than, so our pivot actually equals the left, right? So our pivot equals the left in this case, and it is not equal to the target. So that's our case where, if our pivot value equals our left value, we're just going to say, let's just increment our left because we don't need to do it. We can't do a binary search. Because like, yeah, sure, in this case, we're here and this is the first value, but we could have easily been in one of these, right? Where you don't know where to go. So if our pivot is 2, we're actually going to increment our left over here. And now our left and our right are out of bounds. So now we don't have any more values, so we can return false. Okay. So now let's go through this example and let's maybe find some some small parts of it essentially. Oops. Didn't mean to do that. So let's just get rid of all this. Get rid of this. Get rid of this. Okay, so let's say we have this example, but maybe we have, let's say we're looking for a 0, and maybe it's over here, right? And let's actually get rid of this pivot value because it might be something different, but okay. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8 total indices. So our pivot value should actually be over here. And so you're going to have something like this. This is like one of the test cases, something along these lines. So essentially what we're going to do in this case is we're going to say, okay, is our pivot equal to our target? No, it's not. Is our pivot equal to our left? Yes, it is. So we're going to just say, while the pivot's equal to the left, let's just keep increasing the left because it's a value we don't care about. And so we're going to say like, okay, and also we're going to also make sure that the left isn't out of bounds, right? So we're going to do it until the left is out of bounds. So we're going to say like, okay, the pivot's equal to the left here. Let's just increase the left over here. Is it still equal? Yes. Let's keep increasing. Keep increasing. And you can see like, even though we went past the pivot, it doesn't really matter because all of these ones we don't care about. This one can't be the target because we checked that first. So we're going to go over here, and then we're going to finally go over here, and then we're going to have a value that we do care about. And then we're going to say at the end of the while loop, let's just continue on to the next iteration of the binary search. So here, our left is going to be here, and we're going to say like, okay, we're out of the while loop. Let's just continue on like back to the beginning of the binary search. So now we're going to check. So we're going to have a left over here actually. So our pivot now is going to be this. And we're going to check, okay, is the pivot equal to the target? No, it's not. Okay. Is the pivot, yeah, so the pivot is not greater than the target. Is the pivot equal to the left value? No, it's not. Okay. Is the pivot greater than the left value? Yes, it is. So that means it is on this part of the array, which it is, right? For this subarray, it would be. And is the target greater than or equal to the left value? So the target actually equals the left value, right? So it's not greater than, but it is equal. So it is on this part. It is on this part. So for the target, we're going to check, is it greater than or equal to the left value? As you can see, you need it to here. So it has to be on this part. It can't be on the right part. Actually, sorry, it can be on the right part, but it doesn't matter. If it's on the right part, it has to be on the left as well, because you would need some array like 0, 1, and then you would need like 0 or something, right? In which case it would actually be, so you could have an array like this, in which case your target would be on both parts, but that doesn't really matter because, so if it was like this, 0, 1, 0, 0, your target would be on both parts. So if your target was 0, it would be on both, but it's guaranteed to be on the left. So if we can just say like, well, it's on the left and the right, let's just focus on the left. So it doesn't really matter that it's on both. Okay. So our target has to be here. And so now so if our pivot and our target are both here, right? Now we just say like, where are they comparatively to each other? So our pivot is here. Our pivot value is 1. Our target is 0. So our target is smaller than the pivot. So we need to make the left, we need to take the left side of the array. So essentially we need to get rid of this and we need to take this part of the array. And we're going to make our right value here. And then finally, our pivot value is going to equal to the target now. So we're going to return true. So that's like the main thing we have to do from this problem compared to the other problem is we're going to, if the pivot is equal to the left, we're just going to keep increasing the left until it's not. And we are guaranteed to like get rid of all these values. And then finally, once it's not, you could also do this. You could do this in an if statement. Either one works. You could do it in a while loop if statement. It's the same thing, the same time complexity. Like if you have a while loop for your binary search and you just have an if that says like left plus 1 and then continue or something, it's the same complexity as having a while loop and a while loop in there to do left plus 1, right? It's literally the same thing. So there's a bunch of ways to do this problem. And the reason I'm not a big fan of this problem is because actually, if you, I guess we have enough to start coding, so I'm going to show you why. So actually, if you can literally just say like return target in nums, and this is actually, believe it or not, should pass, and it should actually be efficient according to LeetCode. So that's why, like, or at least sometimes it is. So you can see like, oh, look, you have a great solution here. It's all in here, but it's great. So the test cases like that LeetCode gives you for this problem aren't the best, and like it's kind of hard to test. Is your solution good? So maybe they should have like made some better test cases to like test like for, you know, how often are you actually using a binary search and how efficient your solution is. Because yeah, this reminds me of when I actually made like a queue in JavaScript that was like faster than the JavaScript queue, and then I tried some LeetCode problems where my queue pops were O of 1 and the JavaScript queues are O of n, and it was still like giving me more time on LeetCode. So I was like, okay, is there something wrong with my queue? What's going on? But then when I did try it with like a huge data set, it actually worked really well. It worked like a Python deck roughly. Okay, so let's go through this. So we have a left and we have our right. So our left is going to be 0, our right is going to be nums minus 1. Then we're going to have the binary search. And then we're going to have a pivot. And so we're going to check if the pivot is equal to the target in the beginning. So we're going to say if nums pivot equals target, let's just return true, right? Because we found our value. Okay. So now we're going to say if nums pivot is the left value, this is the part where we're going to keep incrementing the left value until it's not. So we can just say like while, and we are going to check to make sure the left isn't out of bounds as well, because we could have an out of bounds error. Like let's say this whole thing is like 1, 1, 1, 1, 1, 1, 1, you know, you would go out of bounds. So you want to make sure you're not out of bounds as well. And nums pivot equals nums left. So while they are the same, let's just keep incrementing it. And then when that's done, we actually want to continue because we want to, like, when they're different, we actually want to get a new pivot and compare it to the target and stuff. So we're just going to do this while loop, and then we're going to continue to make sure that we do this part again. Okay. And yeah, for like actual efficiency, it doesn't matter technically, I guess, where you write this code, because if this is the part that repeats a lot, you're going to want that near the top as opposed to the binary search region. And I guess those are like small things. You know, if any of you have taken like a like computer architecture class, you know that like you can have the exact same code and it's literally just like the order of your stuff actually makes a reasonable difference. It's not going to change sign complexity, but it will change, like for something like if you write like sorted algorithms or something, it will change it. Okay. And the sorted algorithm, if it's like 1.5 times as fast as something, actually makes a really big difference in the real world, not in a LeetCode problem. Okay. So if the pivot location is going to be like where the pivot is in the array, it's either going to be in the left or the right, and we're going to represent the left as a Boolean value. So we're going to say if nums left is less than or equal to nums pivot. So I guess technically you don't really need a equal to, because if it's equal, we're just going to keep increasing this. But essentially, we're just checking, is our pivot in the left part, like for our array, is it over here or is it over here? And we're going to represent this with true, and we're going to represent this side with false. So that's what we're doing there. So we're going to have pivot location, and now we're going to have a target location. And as I showed you from the other problem, the target can actually equal nums left, so you do have to actually check for that. So nums left less than or equal to target. Okay, and then now we simply have two cases. So first, let's handle the case where they're in different sides of the array. The pivot location does not equal target location. So we're going to first check if the pivot is on the left side of the array. So if pivot location, so this should just be true. So if pivot location is this, that means this is on the left side of the array. So if this is on the left side of the array, we want to go right. So we're going to go right. Otherwise, the pivot's on the right side of the array and the target's on the left, in which case we want to go left. Okay, and so our other case is if the pivot and target are in the same exact part, then we just do like a normal binary search where we just check like if the target is greater than or equal to the pivot or less than. So if the target is greater than the pivot, it can't be equal because we already checked for that. So let's make some more space here. There we go. Okay, so if the target is greater than the pivot, then we want to go right. Otherwise, we want to go left. Oh yeah, we also want to return false if we went through this whole loop and we didn't find anything, right? That means we didn't find our target. Okay. Left. Okay. Yeah, looks like it passed. So, like I said, it's totally random on like efficiency, so I wouldn't worry about like these numbers. Like you can see, like it's all over the place. Okay, so let's actually just go through the time and space complexity. And I actually want to bring this down. Okay. So for the time, what are we actually doing here? So obviously, worst case scenario, like we are binary searching when we can, but then when we're reaching numbers that are equal to the left, we're not. So actually, worst case scenario, it would still be O of n, because like if your numbers were just like a bunch of ones, right? If it was like this, you would basically do this while loop n times. So that would be O of n. So worst case scenario, it's O of n, but maybe you can argue like average case, it's O of log n, because we are still doing binary searches when we can, but then when we can't, we are doing a linear search. And for the space, so we have a left and a right and a pivot, but we don't actually have in like pivot locations and target locations, but we don't actually have any, you know, dynamic memory. We don't have any arrays or anything, so this is going to be O of 1. But yeah, this is going to be all for this problem. Like I said, the complexity, or not the complexity, but like this, what it gives you in LeetCode is not going to be super descriptive of how well your algorithm is actually doing, because first of all, it changes a lot. Second of all, like I showed you, my linear solution was, you know, like it gave me something like this for a linear solution, which is like doesn't make much sense, right? Because that would be like the worst one technically. Because I think the tests that actually take the most time are basically in a linear solution. So if you just have tests that are mostly like this, then actually, if you think about it, a linear solution would be the most efficient because it wouldn't have all these things in here. So it would just be a lot less code. So this would, like, if you had something like this, then if you did have just like go through it linearly and look for the number, that would be the fastest. But if you had a lot less duplicates, then as you know, as the number of duplicates goes down and down and down, then the binary search solution will go up. So it would be some kind of graph of like where, you know, if it was all one number, the linear solution would actually be a little bit faster. But as you have less and less duplicates until you finally have all different numbers in a big array, then this would start beating it by a lot. Okay, but that's going to be all for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.